Hi class, this video is on topic D4, electricity and magnetic fields, and we're going to be talking today about right-hand rules number 1 and 2. So when we think about the direction of electricity, we could think about conventional current or electron flow. And just a reminder that in this course, we are going to be using conventional current, the current going from the positive terminal of the battery to the negative. And also recall that we have 3 properties of magnetic field lines that were the focus of last video. One is that magnetic field lines are north to south outside of the magnet. The next is that the lines are closer together where the force is strongest, which is where near the poles. So the closer to the poles you are, the more force of attraction or repulsion you would experience as a magnetic object placed there, and the line density is higher. Magnetic fields also never cross. Note that magnetic field lines also tell you the direction that a north compass needle would point if placed at that location. So one way to sort of determine the map that is the magnetic field line diagram is to place a bunch of compass needles around a magnet, and then sort of to connect those line segments. This is important in answering some of the questions that will come up in the homework today, because sometimes it will be an compass face, and the purpose of the question is to determine the direction of the compass needle, which is exactly the same as asking what is the direction of the magnetic field line at that specific location. So we're going to talk first about Ørsted's discovery, which is the first time we're really seeing a connection between electricity and magnetism. And right-hand rule number 1 is going to give us sort of a mnemonic device to remember his observation. And this is a circuit picture of that observation. So Ørsted proved that electricity and magnetism are linked, and that a straight conductor with current running through it creates a circular magnetic field around the conductor. So we're talking about a straight conductor. We're talking about a wire with current running through it. So we take a wire and we send current through it. So he noticed that before he sent current through the wire, so this is your wire, he placed compass needles around the wire and noticed that all of the compass needles point to where Santa lives, so Earth's geographic North Pole, which we know is Earth's south magnetic pole. So the compass needles all point the same way if there is no current passing through it. Then when Ørsted turned on the current, or turned on the, closed the circuit so that there was current running through this wire, the compass needles changed direction such that they formed a complete circle. So if you notice this the red needle is pointing, no 2 positions have the same red needle direction. In the case of this diagram, if the conventional current was going up, the circle forms a, what would that be? Counterclockwise circle. And here are a few statements that summarize his experiment observations. When the direction of the electric current is reversed, the magnetic field is reversed. So this is the current, the wire with no current. The compass just points where it normally would to Earth's north geographic pole. Then when the current is when the current is in this direction here, the compass needle is deflected, in this case to the left. When we switch that current direction, the compass needle points to the right. The magnetic force created by the current is perpendicular to the direction of the conventional current. So again, no electricity, no unusual deflection of the compass needle. But when we do have electric current running through the wire, the compass needle is deflected and it moves so that it's 90 degrees to the direction of the current. So if the current is up and down, and we're looking at placing the compass in front of the compass needle would be going left to right. Ørsted's discovery can be used to control the strength and direction of magnetic fields, which is very powerful. So you can remember the patterns observed by Ørsted's discovery by memorizing this right-hand rule number 1, which is called right-hand rule for a straight conductor. So it's just a straight wire. So when the thumb points in the direction of the conventional current, the curled fingers show the direction of the magnetic field. So for the right-hand rules, as you might have guessed, you need to use your right hand. So you're gonna put down your pencil and you're gonna take your hand and you're gonna form this kind of like thumbs up hand gesture. And then you're always gonna point your thumb to the current direction. That's conventional current direction, so positive terminal to negative. And then your curled fingers are going to be the direction of those magnetic field circle lines. So we can use this new mnemonic device, right-hand rule for a straight conductor, to determine the direction of the magnetic field lines if we're given the current, or to determine the direction of the current given the magnetic field line. So there's 2 variables. We need to have one to solve for the other. And because we're working on problems in 3-dimensional space, but we're drawing it in 2-dimensional paper, let's establish a commonly used convention in math and science. So if the concentric circles of the magnetic field lines are flat on the page like this or this, and we know that the current is 90 degrees to it, our options are in or out of the page. So if the circle is lying flat on the page, we have to be able to show that the current is coming out of the page or into the page. So into the page is an X. So into the page is an X, and out of the page is a dot. So there's kind of a visual that I use to help me remember which is which. So let's say if you imagine that there is that you send an arrow down the inside of your copper wire. So this is sort of like representing your current going into the wire, and you can see the outline of the wire if you're looking at the other side. If someone shoots an arrow at you through this wire, what are you gonna see as the cross-sectional area? So if you cut that wire right here, you're gonna see inside that circle where it represents the outside of the wire, you're gonna see the tip of that arrow pointing at you. So that's how you get that out of the page is a dot. Well, it's not where it comes from, but this is a visual that helps me. Now, on the other hand, let's say you are the one that is shooting that arrow. The back of the arrow has, let's say you're angry. So you're shooting this arrow away from you. You see those feathers that kind of make like an X. If you look down this length, you will see an X. So that's how you could perhaps, maybe this would help you too, to remember that into the page is an X. So into the page is an X, and out of the page is a dot. And I just want to take this opportunity with this nice flat, with this view where the concentric circles are nice and flat, to point out something. So notice that the concentric circles are not equally placed, and the question is, should they be? So should the distance between this and this be exactly the same as that? So recall that the line density in field diagrams tells you the strength of the force. So if you put a compass needle really close to the wire, there is a strong magnetic force of attraction or repulsion, or I guess there's a strong force deflecting the compass needle here. Whereas the further out you put your compass, the weaker that force of attraction or repulsion is. Therefore, the more spaced out the circles should be. So these circles not being the same distance from here to here versus here to here versus here to here, that is not a mistake. That is deliberate and important. Okay, so let's try an example. And the question is asking us to draw the compass needles. So let's say we have a current carrying wire, and we are gonna put our compass somewhere around this wire, or maybe we have 6 compasses, we'll place them all around, and we wanna know what will be the direction of the wire. So since we're given conventional current, we're asked for magnetic field lines, so we're given the direction that our thumb should go. So you're gonna give yourself like a thumbs up or face your thumbs up towards the screen. Your thumb is going to go upwards, and then you're gonna observe your curled fingers. So notice how your fingernails are on this side are like curled up into your palm. So the magnetic field lines would be upwards. Notice how over here, the section of your fingers is going to the right. And then notice the section where your knuckles, where your fingers meet your knuckles, they're going like out of the page or down. So that would be our final diagram for how the compass needles will look when the current is turned on, such that here is positive and here is negative. So for part B, we do the same thing. We're given the current, so you direct your thumb down. So you're gonna do a thumbs down, and notice your curled fingers will tell you over here, your fingers are going kind of out of the page or down. Here, your fingers are kind of going into your palm or up, if you draw it in 3D. So your fingers are curving that way, and that would be our diagram. So make sure, once again, note, are you right-handed? If you are right-handed, you need to put down your pencil, figure it out with your hand, and then pick up your pencil to draw on the answer. If you're left-handed, you have a slight advantage here. So let's try another example. In this case, you're given the magnetic field lines. So you're given the direction that your fingers should curl, and you're asked for the direction of the current. So you're asked for the conventional current, which is indicated by the thumb. And since this circle is lying flat on the page, your wire is either showing a current going in or out. So it's either an X or a dot. So you can guess 50-50, but hopefully you remember right-hand rule number 1 to take that 50% to 100%. So you're gonna, I tried to look for an emoji that shows this, but it doesn't quite exist. So let's say you do your thumbs up, but now I want you to rotate at the wrist so you're looking down your fingernail. Notice how your fingers are curling counterclockwise. Counterclockwise, like this one. If your fingernail is pointing at you, that's out of the page. So you're gonna put a dot here. And similarly, if you rotate your wrist so that the thumb is pointing away from you, you sort of see the edge of your pinky and it's curled. So that would be, you see that the magnetic field lines of your fingers are clockwise and your thumb is pointing into the page, so you indicate that with an X. Okay. So that was right-hand rule number 1 for when the wire is straight. Now we're going to talk about solenoids if the wire is wrapped around like a spiral. So we could call this a coil or a solenoid. And you might wonder, why would we wrap it around? But maybe if you've ever taken apart a motor before, maybe some small electronic, you would see like a spool of copper with many, many, many turns. So we definitely make use of this, the applications of this solenoid's electromagnet more than we would if the wire was a straight line, because the magnet is not very strong. We can actually make a much stronger magnet and do a lot more useful things if it's a solenoid. So let's first talk about where this observation was made. Why should we make it into a spiral? So magnetic fields created by current carrying wire interact in the same way that magnetic fields from permanent magnets interact. So we know that 2 north poles repel, but if we actually look at the magnetic field lines, the neighboring magnetic field lines are the same, which means there's repulsion. And that's actually the same thing. If we take 2 parallel wires, they're going to create their own magnetic fields and interact similarly. So neighboring magnetic field lines repel, and therefore there's a force of repulsion. So Ampere was the one who discovered this. Ampere took Ørsted's experiment a step further by seeing how magnetic fields in two parallel current carrying wires interact. So in this case, the current is traveling this way. Here, the current is traveling that way. There's going to be two magnetic field line circles that are in different directions. It's going to cause the force of repulsion. So the observation is summarized by the following two statements. Two parallel wires with opposing current direction will repel. Two parallel wires with the same direction will attract. So if you're like me, you might pick out opposite, repel, same, attract. You might say, well, that's not very intuitive because we have the law of magnetic poles, which says that opposites attract and like poles repel. So what I would suggest, either memorize this set of statements, or always use right-hand rule number 1 for a straight conductor and look at your neighboring magnetic field lines. The magnetic field lines here are in the same direction, therefore there's a repulsive force. Here the magnetic field lines, the neighboring ones, are in opposite directions, there's an attractive force. Running through a, oops, my words are gone off of the screen. Running current through a coil creates a solenoid, which creates a magnetic field that is similar to that of a permanent bar magnet. So each piece of wire is gonna have these clockwise magnetic field lines. And they're actually gonna add up when you get far enough away from the wire, so that all of the magnetic field lines on the inside are all pointing to the left and they're all additive. So this is why creating the coil is gonna be a stronger magnetic force than if we just had one wire. And if you take a look at something that's that shape that has a north side here and a south side here, remember that magnetic field lines go north to south. On the inside of a magnet, they go south to north, and then on the outside of the magnet, they go north to south. So that actually looks like a bar magnet. So see how this line here very much looks like that line there. So an electromagnet is any device that produces a magnetic field as a result of an electric current. So remember that we only create these magnetic field lines, or this overall like electromagnet, if the current is on. When we turn off the current, there's no magnet. So a solenoid is a cylindrical coil of water acting as a magnet when carrying electric current. And an electromagnet is any device that produces a magnetic field as a result of current. We have right-hand rule number 2 as a mnemonic device to remember what happens with a coil. So when we curl our fingers to match the direction of conventional current, which is positive to negative, the thumb points to the north magnetic pole. And because we're completing diagrams for something that's in 3D, but we're putting it on 2D paper, it's really important to start visualizing the coil as a spiral in 3D. And when you have to draw a coil, make sure you're making it clear which piece of wire is in front and which one is behind. So it's where they overlap. They can't just be in intersecting lines. You have to show one that is closer to you than the other. And always noting where is the positive side of the battery and where is the negative side, because just as much as I could travel along the spiral like that, you could travel along this exact same spiral like that if this was the positive end. So you have to visualize 3D and note where the positive side is in order for you to solve any of these diagrams. Just taking a close look, you can do the cross section of this spiral, and you would see that if this side is the positive side, when you get here, we're going into the page, and when you get here, we're going out of the page. So you have parallel wires out of the page on the top and into the page at the bottom. Okay, so I always say when two things are confusingly similar, put them side to side so you can highlight the similarities and the differences. Right-hand rule number 1 and right-hand rule number 2 are very similar, but we use them in different places. So we use, for a straight wire, right-hand rule number 1. Right-hand rule number 2 is for a coil or a solenoid. And what does it look like? Okay, so we've got straight wire or a coil. What does your hand look like when you're applying right-hand rule number 1? It looks like that. What about when you're applying right-hand rule number 2? Uh-oh, it looks like that. So it's exactly the same hand gesture, but you might be rotating through the forearm. You always want to rotate so that your thumb is showing you the current. And here you want your thumb to show the north side of the magnet as if this was a bar magnet on this electromagnet. So for conventional current, your thumb points positive to negative. So the thumb is the conventional current for right-hand rule number 1, but for right-hand rule number 2, you have curled fingers that give you the direction of the conventional current. And in terms of what you get, like sort of what magnetic information you get, the curled fingers give you the magnetic field line for right-hand rule number 1, and the thumb points to the north side of the bar magnet for right-hand rule number 2. So you can see there's a lot that are similar, like especially if I were to watch you do a problem and you were not to say anything out loud, I wouldn't know if you were doing a right-hand rule number 1 problem or 2. They look very similar, but you can't just write on your thumb current because, you know, your thumb means current in one and it means the north magnet in the other. Okay, so let's talk about why an electromagnet. So how is an electromagnet different than a permanent magnet? Electromagnets can be turned on and off easily. So we just turn on the current and we have an electromagnet, turn off the current or open the switch or like open the circuit, and now we don't have a magnet. So that has a lot of advantages. And then the power of an electromagnet can be adjusted. We can have a more powerful electromagnet if we have more loops, if we design the electromagnet with more loops, or if we increase the current. So we would do that maybe a variable power supply. So we dial up the voltage and that would increase the current. Or we could wrap that coil around a soft iron armature. So if there's any material that's easily magnetized, it would be best to be put at the center to have a more strong magnet. So that's all for this video topic. You have a select number of questions. A lot of them are diagram based. So I encourage you to redraw the diagram in your notebook, being mindful of the adjustments, the tips that I've given you for showing 3D situations on 2D paper. And there is an optional worksheet on right-hand rules number 1 and 2 in the standard notes package for this unit. So I'll leave that as optional for you. Sometimes when you're doing these questions, students don't know like what you're looking for. So I just thought I would pull up some randomly and just double check if we understand what's being asked. So here we have parallel wires. Are they both going the same direction, or was one going into the page or one out of the page? So we're given the magnetic field lines, and notice that these magnetic field lines are going the same direction, so there would be repulsion. So what two parallel currents will be repulsion? Is it their same direction or opposite? Here, we've got an electromagnet, so the spiral is going this way, positive to negative. We're asked for which side is north and which side is south. Here, we're asked to draw magnetic field lines and determine if there's attraction or repulsion. Here, you're being asked what side is the north or the south side. And how did I know this? I just looked at what is the given information, either information about current or magnet, and then I'm looking for the other one. So in this case, I'm given information about current, although you might not realize it at first. So this is the positive side of the battery. So no, I know I'm wrapping like this. So I'm going from here to here, positive to negative, and I'm looking for a piece of information about the magnetic field. If you're given a compass needle face, but you're not given the needle, obviously you're looking for the direction of the compass needle. So that's what direction will the north side of the compass needle point. I do recommend just a simple arrow. Don't try and do one of those triangle compass needles that's like more accurate. Just draw an arrow. And the worksheet for right-hand rules number 1 and 2. So this is just practice makes perfect. So it's a bunch of similar problems in a row. Notice when you get to here, it does get tricky. It's the wrapping direction and whether it's positive or negative on which side. There's 4 different combinations. You could wrap it one way or another, and this could be coming from the front or the back. So these can get a little bit confusing, but it just really helps to visualize. So maybe if you have a long wire that's like your headphone, if you have the headphones that are wired, or maybe just a string or a rubber band, if you could take a pencil and just wrap one direction around the pencil to help you visualize how there might be different scenarios here, because they all kind of look the same, but they could be different answers. Okay, so don't forget to submit the exit ticket for this lesson, and submit the practice questions once you have completed them. Have a great day.